hospitality. It's always wonderful to be back in TIFR. I'm going to tell you about some work that should be coming out next year, meaning tomorrow. And I'll introduce my collaborators. We've been lucky to have in Cambridge for the last year. Hey, Sandeep, how are you? Very good to see you. Great to see you. We've been very lucky to have in Cambridge for the past year two fantastic postdocs. Pietro was a student in Oxford with James Sparks and joined us a little over a year ago. Masazumi, you guys may know because he was in HRI for 3 years. And he's about to start a job, a faculty job in Yukawa Institute in March. Also on the paper, we have Hee-Chol Kim, who's just started a faculty position in Pohang, and Kumran Vafa. I should say that from my perspective, these two are the ones that just did months and months of horrible calculations, none of which are going to be in evidence in the board. This is one of these projects where you calculate, and in the end you find there were very, very slick arguments that you should have realized at the beginning to give everything. But all the hard calculations were done by Pietro and Masazumi. All right, if there are experts in the room, I'll tell you what we've done in one sentence. We've taken a very particular 5D supersymmetric fixed point and broken supersymmetry and try to understand where we go at strong coupling without supersymmetry. Okay, that's what it's about. For those of you who haven't looked at 5D theories before, I can give you a slightly bigger picture. I think it's true to say that for most of the 20th century, people thought that quantum field theories didn't exist in 5 dimensions or higher. And the reason is that if you write down an action for quantum field theory, in 5 dimensions and higher, the coupling always gets stronger as you go to higher energies, and the theories are always non-renormalizable. So it was thought, albeit in a slightly old-fashioned way, that there was no way to make sense of quantum field theories in 5 dimensions. That changed in the 90s. It changed because of developments in string theory, and I think it was Seiberg who was mostly pushing this. He realized that string theory arguments told you that there were novel, non-gravitational, interacting conformal field theories in 5 dimensions and also in 6 dimensions. So the current folklore, although I don't think there's a huge amount of evidence to support this, is that quantum field theories exist up to 6 dimensions, but not any higher. The reason for this is just that we haven't found any higher than that. So Seiberg's constructions of these quantum field theories were somewhat abstract. They certainly weren't Lagrangians. In fact, it's known that these theories do not have Lagrangian descriptions. They're non-Lagrangian quantum field theories that are strongly coupled. Nonetheless, because of the magic of supersymmetry, and because for the last 20 years or so there have been many very clever people who, for some reason, have had nothing better to do than study these theories, we know an awful lot about these supersymmetric theories. In contrast, we know almost nothing about the existence of non-supersymmetric quantum field theories in 5 dimensions. And what I really mean by this is conformal field theories, so fixed points which you can then deform and flow away from and understand the phase space of such theories. The state of the art, as far as I'm aware, is the following. There's a beautiful paper by Peskin from, I think, 1980, certainly early 1980s. Peskin redoes the analysis of Polyakov. So Polyakov has a very famous paper from the 1970s who does a 2 plus epsilon expansion of the sigma model in 2 dimensions, of an ON model. In 2 dimensions, the sigma model, say the ON model or the CPN model, is asymptotically free, but in 2 plus epsilon it's not, and you can play off the one loop term versus the epsilon term and find a UV fixed point of the sigma model in 2 plus epsilon dimensions. Then you can move up to epsilon equals 1 and you find the Wilson-Fisher fixed point. So Peskin tried to do the same thing for Yang-Mills. It's completely obvious, it's 2-line calculation, that Yang-Mills has a UV fixed point in 4 plus epsilon dimensions. And then the real question is, can you trust that as you move up to epsilon equals 1 and believe that there genuinely is an interacting field theory there? As far as I know, this really hasn't been pushed very, very much. I mean, this paper doesn't have many citations, and I think it's still an open question. Is there an interacting fixed point of just pure Yang-Mills? All right, more.
Sorry,
Yes, Sandy.
Sorry to ask such a remedial question, and you probably might talk more about it, but to some extent the evidence for these supersymmetric fixed points and so on in Heidi comes also from brain constructions or related ideas
absolutely.
and so on.
Yeah.
And now, could you think of a brain construction, say, in a background, or by suitably just thinking of brain curves which break supersymmetry, and then argue that way as to whether you might have interesting fixed points in Heidi?
Better than that. So there's some unpublished work by one of Cumberland's students who shows that if you take any of these Hanani-Witten type brain constructions and break supersymmetry, the whole thing is unstable. There's a runaway mode and the whole thing just explodes. So the answer there is very clearly no, it's not possible to find non-supersymmetric fixed points in a brainy way.
Although you could do other things.
You could do other things, yeah. No one's managed to do this. I should also say no one's managed to do this for say 2+1 dimensions, where in recent years we've developed huge amounts of control over what happens when you break supersymmetry. Say, take say mirror theories in 2+1 dimensions. Supersymmetric duality breaks supersymmetry. We now know exactly what happens, but not using brain constructions or string theory ideas. You know, those brain descriptions were always in a region of parameter space where you weren't really describing the field theory. You know, when you drew those pretty geometric pictures, you weren't in the field theory regime, you were in some other regime where there are all sorts of, 10-dimensional gravity effects that were interacting, but the things you could compute were the BPS things, and they didn't care which regime you were in, so you thought those geometric pictures were telling you something real about the field theory, whereas they were just telling you about the BPS.
You mean even the stuff? Or even more?
Then you could bring them together and so on, so forth, like the Witten's Hanani stuff.
Yeah, so let's take Hanani-Witten. You want to draw a picture like this, but the field theory limit is where the separation of the brains is smaller than L string, basically, because you don't want those Kaluza-Klein modes on that D3 brain and blah blah blah. As soon as you go to that regime, you really lose all control, especially when you break supersymmetry.
Another immediate question. So how is it that in 2+1 makes a connection between 2+epsilon dimensions and 3 dimensions, or 4 minus epsilon dimensions and 3 dimensions all the way? How is it that these are extrapolated to argue that is the limit in the limiting case of epsilon going to 1?
Can I answer the question in the low dimension case where it's Wilson-Fisher?
No, I'm saying even when a case which is presumably understood, which is the 2+ epsilon dimension or 4 minus epsilon dimension, and the epsilon going to 1 limit is supposed to be the Wilson-Fisher fixed, the Ising model.
Yeah.
In 3D, how is it established?
Oh, and I think you just cross your fingers and hope is the real answer.
Just the symmetry
You have the RG diagram, and there's a level of topology in the RG diagram. You have the Gaussian fixed point, which is unstable, the Wilson-Fisher fixed point, which is stable. When epsilon is very small, they're close to each other, you draw the flows, and then you might hope that topology in RG space is stable as you crank up epsilon and these things get further apart, and you can no longer trust it.
It could be that at epsilon going to 1, it may go to a different fixed point than the Ising model say.
It may go to a different fixed point. There could be some other fixed point which comes out of nowhere that you had no control on, which annihilates that one, and all sorts of things can happen. And I think we know enough about the Wilson-Fisher fixed point to know these things don't happen. But in 4 plus epsilon, yeah, we just don't know. I should also comment, although it's not directly relevant for this work, that there was some very nice work by Klebanoff and collaborators maybe 5 years ago. They looked at ON models. They did 4 plus epsilon expansions, 6 minus epsilon expansions. They argued that there were novel fixed points in 5 dimensions if n was sufficiently large. Where and I might be misremembering, I think sufficiently large meant of order 30, and then there was another fixed point where it was only n of order 1,000 or something. There was something a little unusual. And then the bootstrap people started looking at this, and they indeed found kinks in their kinky space. The kink corresponded more or less to where the ON people had. So there is some mild evidence. I think mild is maybe too weak. Some fairly decent evidence that the ON model, that there are fixed points in 5 dimensions. All right, and it would be very nice to have some global picture about which theories exist in 5 dimensions and which don't. What I'm going to say here doesn't really obviously make contact with any of these these fixed points. In particular, there are going to be fermions involved that will be crucial, and it seems unlikely that these are related to these bosonic fixed points that Peskin and Klebanov and others have discovered. But it would be nice just to get the picture of what exists.
Klebanov's fixed points had no gauge fields, right?
No, they were just ON models. Yeah. All right, so the theory I'm going to consider is the simplest theory in 5 dimensions. You can think of it as the UV completion of SU2 supersymmetric Yang-Mills. So it's SU2, n equals 1. Super Yang-Mills, this means 8 supercharges in 5 dimensions. The action, there's a gauge coupling which sits out front, and a trace over the SU2 gauge group, and then there's the field strength. There's a real scalar field, phi. There's a fermion. I'll say a little bit more about this later. There's a Yukawa term, which is not going to be so important for us. And there's also the D terms that you usually integrate out, but I'll keep for a reason that will become clear later. All right, so that's just SU2 Yang-Mills. One important point, this is what's called a symplectic Majorana spinner in 5 dimensions. It means you take a Dirac spinner, which is 4 components, and a second Dirac spinner, and then you impose a reality condition between those Dirac spinners. For our purposes, all we really need to know is that there's a global symmetry which acts on these fermions. And the global symmetry in this context is called SU2R. It's the R symmetry of the SU2R symmetry of all theories with 8 supercharges. That's how it manifests itself here.
That's actually USB.
Oh, man. USP.
Well, SP1.
That's the same as SU2, isn't it? There's no global difference between the two.
Higher supersymmetries, the corresponding asymmetry would be asymplectical, but I'm not a unity. That's the.
Oh, I see. Okay, but here they really are the same.
Here they are.
Okay, very good. Yeah. All right. The theory is non-renormalizable. This gauge coupling dictates the scale of the theory. 1 over g squared is an energy scale. If you're below that scale in the infrared, everything's weakly coupled. If you're above that scale, you have no idea what's going on. The theory is just strongly coupled. Almost certainly needs new degrees of freedom to make sense of what's going on. One other symmetry which is important, there's a topological symmetry. This topological symmetry is going to be called U1I. I for instanton, and it has a current, which, well, there's a 1 over 8 pi squared that I won't bore you with. But this is the current written as a 1 form. So there are Yang-Mills instantons. Yang-Mills instantons obey the equation F equals star F. They're codimension 4 objects, which means they're particle-like objects in this system. They're localized in space, but have a world line in time. This current is the current that counts the number of instantons that you have in your system.
Sorry, David, I was trying to understand the 4 plus epsilon.
Yeah.
So is it this that you take the theory with the scalars, then you do phi bar phi sigma, and then you perturb with alpha sigma squared? It's the relevant operator. The Wilson-Fisher fixed point in 4 minus epsilon directions has no relevant deformation other than mass. But the Wilson-Fisher fixed point in 4 plus epsilon dimensions would have a relevant deformation. So is that the idea?
I don't know. Yeah.
I think it must be, because you can't do it phi to the 4, because that's irrelevant.
Yeah.
I think it must be sigma squared. I think you do
What is sigma? Sorry.
take the
Grunge multiplier.
phi bar phi, take phi bar phi sigma plus sigma squared. I think that in 4 plus epsilon must be a relevant definition, which then follows.
I see. That sounds reasonable.
Okay.
That's different from integrating sigma out in this sigma.
Yeah, you don't put a phi bar phi to the 4. I mean phi bar phi squared, because that would not work. Yeah. Because free theory has a relevant deformation below 4 dimensions. I'm sorry, but above 5 dimensions it becomes irrelevant. But I think it flips for the Wilson-Fisher. The Wilson-Fisher had no relevant deformation below 4 dimensions, because it was an endpoint. But now we'll develop one above 4 dimensions.
Oh, I see what you're saying. Yes, yes. Okay, good.
Search for a 6 point upward also.
It's not. I just want to say what was the conjecture theory.
Yeah.
Then we can talk about when it exists.
It's a UV fixed point.
Yeah. The Wilson Fisher now becomes a UV fixed point above 4 image.
Yeah.
It was an IR fixed point below 4 image.
Yeah, but that's also fine. But I mean, here also, for example, you would look presumably not UV.
Absolutely. I'm just trying to understand what is the 4 plus epsilon of what? I think this is the theory.
There'll be no epsilon in this talk
What? Yeah.
anymore. Yeah. All right. So this is non-normalizable. It does have a UV completion. This is in the class of theories that in Seiberg's original '96 paper, he told us that there was a fixed point. The fixed point has. I'm going to elaborate on this diagram as I go on. So, all right. So the fixed point is called the E1 fixed point. It's one of these terribly boring names. It's the first in a. Actually, it's sort of the second. There's a zeroth, but it's the first in a sequence of fixed points labeled by E8. So it's a superconformal field theory in 5 dimensions. I'll tell you a little bit more about it shortly. There's a relevance operator that you can turn on. I'll also tell you a little bit more about that shortly. If you turn it on, the theory flows to super Yang-Mills. In other words, it flows to this theory here. Of course, if you follow the flow all the way, it's strictly speaking just a bunch of free fields. If you're close to this point at 1 over g squared, the interactions turn on.
So you start with E1 and follow this relevant direction and you end up with this theory?
Yeah, so this E1 fixed point should be thought of as the UV completion of this theory. Yeah. Let me just mention, again, I'll flesh this out shortly. You turn on a relevance operator with a particular coefficient. The coefficient is going to be called H. By the time you get down here, H manifests itself as 1 over g squared. In other words, it's the scale of the theory. All right, so this is a SUSY fixed point.
So it's a single relevant operator that preserves n equals 1. It's unique relevant operator.
Almost, and I'll tell you what the almost is very shortly. But, yeah. All right, so the most important thing, and the reason it has this name, is that U1I is enhanced to SU2. So the fixed point actually has 2 SU2 symmetries. There's the SU2R symmetry, but there's also this SU2I symmetry. Something else that's rather nice about this, and I'll explain how all these things are related. If you turn on this operator with the same operator, but with the negative coefficient.
Sorry, how many supercharges does E1 have?
Okay. This has 8. This is, I'm not quite sure how you want to count the superconformal charges, but it's the one with 8.
So 8 plus 8, 16.
Yeah.
There is no more supersymmetry one here.
No,
That's right, because the n equals 2 super Yang-Mills has a UV completion which is 6-dimensional.
yeah. As you said, this unique superconformal at 2 grand 5 dimensions, it has 16.
All right. A rather novel property of this is that if you turn on this same relevant operator but with a negative coefficient, you also flow back to super Yang-Mills. Now with a gauge coupling constant, which is equal to minus h, or maybe I should just say same mod h. So you flow with a plus sign or you flow with a minus sign. You hit exactly the same super Yang-Mills. There's a very simple brane interpretation of why this is. The brane interpretation of super Yang-Mills in a Hernani-Witten diagram. Anybody here is younger than 40, I just apologize now. Hernani-Witten diagrams were cool in the 1990s, that's all I can tell you. All right. This is the Hernani-Witten diagram. This is, what is this? This is an NS5, this is a D5, these are 1, 1, 5 branes. This is the Hernani-Witten diagram for this SU2 Yang-Mills. At the fixed point, it's just this, but then you can sort of open it up the other way and have an SU2 which lives on these branes rather than on these branes. So that's really what the 2 SU2s are. This SU2 lives on the D5s. This SU2 lives on the NS5s. And something rather cute about this is that there are W bosons, at least if you're on the Coulomb branch, and the mass of the W boson is phi, and there are instanton type states whose mass goes as this. Turns out this separation here is 1 over g squared plus phi. And what's W boson here transmutes into an instanton in this language and vice versa. So there's some kind of duality. Duality is one of the most overused words in physics. And this is a different meaning of the word duality than well, any of the other uses in field theory. It's sometimes called a UV duality, but you start from the same fixed point, you flow in two different directions, you end up with the same theory, but where the states in one theory are swapped with the states in the other. W bosons goes to instantons.
Isn't the coupling constant complex somehow? Or is it real?
No, but I'll come to this. It's really a vector, in a way that I will explain. Yeah. All right. For what it's worth, and again, this is going to be useful shortly. The duality works in the following way. It's 1 over g squared goes to minus 1 over g squared. See, g squared is roughly this. Okay, let me not try and elaborate on that. And phi goes to phi plus 1 over g squared. So the spectrum of states is invariant under this shift, which is sometimes called a UV duality.
So the low energy phases with these two deformations are the same.
They're the same, and in fact, this is a little bit if I'm on the Coulomb branch, I go continuously from this to this. Everything happens smoothly. Yeah. If I'm not on the Coulomb branch, I have to go through the fixed point. If I'm on the Coulomb, exactly, that's the point.
I mean, it's just the coupling constant is mod of h, right? So that's 1 over g squared is mod of h. So that's positive, of course, otherwise the Youngman's theory doesn't make sense.
Exactly.
But the spectrum is invariant if you take 1 over g squared and minus 1 over g squared. Is it?
Yeah, because you might think this is true on the Coulomb branch. You might think that the instanton has a 1 over g squared, but actually it's 1 over g squared plus phi. It picks up a one-loop correction, and under this, this spectrum is invariant.
So, in this picture, d5 grains are vertical?
So these are D5s, and these are NS5s. Yeah, I haven't done a sort of duality shift. It's the same as this. All right. Shiraz, as usual, sort of jumped ahead of me a little bit. Let me tell you a little bit more about this H. You suggested it was complex. It's actually a three-dimensional vector. So if we sit at the fixed point, we can look at the superconformal primaries. And there's a slew of operators in the multiplet. You go from one to the other by acting with the supercharge. And the operators look as follows, and it's going to be useful to write down all of them. Oops. All right. So acting with a supercharge does this. The dimensions of these operators are 3, 3.5, and for these two, 4, respectively. So let me tell you what they are. This is a current for the global symmetry. The A index goes from 1, 2, 3, and is the SU2I current. This is the statement that the U1 topological symmetry is enhanced to SU2. This is the current for this SU2. Okay. This is the deformation which, if you add it, it's the relevant operator which, if you add it, preserves supersymmetry. This is also in the adjoint of SU2. This is a fermion. It's not going to concern us. This is another scalar operator. It's clearly another relevant operator. In fact, it's more relevant than this one. But it has two indices. This is an SU2I index, and this is a SU2R index. In other words, if I was to add this operator to the fixed point, it would necessarily break SU2R, but operators that break SU2R also break supersymmetry. So there's two scalar operators, one that transforms under SU2R and one that does not. Adding this one preserves supersymmetry, adding this one breaks supersymmetry.
I mean, that scalar has an I index in it, right?
No, it's got a comma. Sorry. Okay, so this SUSY flow that we...
What does a comma mean? You get both these operators?
You get both these if you act with this. Yeah. So this supersymmetric flow here, you take this fixed point and you add to it the relevant operator that's a scalar and preserves supersymmetry, meaning it doesn't have an SU2R index. Now you can see there's three such operators. They transform in the adjoint of
So
SU2I.
why are those two the same? Not having an SU2R index and preserving supersymmetry. I mean, in a superconformal theory, they have to be the same. But you're breaking conformal invariance. It may turn out to be the same.
True. And actually, I think it's not true because Filiopolis terms break SU2R and preserve supersymmetry. I see. So let me just
work it out.
Yeah. In particular, where I'm going is I'm going to add this, and we'll see that it does break supersymmetry explicitly.
Okay. Yeah. No, I mean he was saying he was connecting breaking R symmetry and breaking supersymmetry.
Yeah. Sorry.
In superconformal theory, that had to be connected. Superconformal theory preserves R symmetry. In a supersymmetric theory, neither.
That's right. All right. The fact that this is an SU2R, SU2I object, immediately tells me why this was true. This H here is actually part of a three-dimensional vector. And I can smoothly go from H positive to H negative just by rotating this vector. So this seems kind of miraculous if you think about this as just one operator. But the fact that you got there earlier, that it's not a real line, but in fact it's a triplet, means that you can rotate around and that these are continuously connected. All right. Any questions?
So basically, it's not the phase diagram won't be 2 points separated by something. It's just 1 point. Right? There's only one low energy phase. This is now the unique n equals 1 relevant deformation. That's not right. Is this the unique relevant deformation?
It's the unique one.
So
What you've said is
true up to symmetry, right?
Is true up to symmetry.
So let's mod out by symmetry.
That modding out by the symmetry is going to be not a wise thing to do where we're going.
Okay, so then it's a sphere. It's a sphere of phases.
You should think about it as a sphere. However, it's going to be very fruitful to think about the projection onto this. One way of saying it is the following: that if I choose the vector in this way, this picks a very particular U1I out of SU2I. And it's useful to think about the phase diagram of the theory with that specific U1I chosen, and not thinking about the parameters that allow that U1I to rotate within a bigger symmetry group. And the reason for that will hopefully become clear as we go on.
Okay.
But I'm going to want to project to this line. Other questions? Yeah, please.
It was probably not well posed, but once we choose an edge of that kind, we pick a certain U1I, which is thought of as the Hitchell-Tong number current in the super.
That's right, yeah.
So the other two generators of SU2I will act as raising and lowering operators for this Hitchell-Tong number. Can you think of it that way? And is the spectrum of this SCFT somehow sensitive to that change in Hitchell-Tong number between different moderate spaces? Can we get more information about the spectrum?
I don't know the answer. I can tell you some related facts that might be useful. the various ways in which you can see this enhancement to SU2I, using slightly more modern methods, are you can compute things like superconformal indices and see that everything combines. You start just with SU2 Yang-Mills. You compute the superconformal index, you see that everything combines into an SU2 invariant. Or Nekrasov partition function is another way. That might be where your suggestion is hidden, but yeah, but I haven't seen it phrased in quite the way you did.
And you compute the superconformal index using the Yang-Mills.
I think that's true. You know better than me. I mean, this is well,
I don't know
Seoc
this
and
theory.
company, but
Yeah, but that's how they usually do it.
what else do they have? Yeah. Okay, so what I want to do is break supersymmetry. And rather than this deformation, I'm going to add to the UV fixed point the following deformation. I'll include this supersymmetric one, but I'll add another one, which is the other operator, which was also relevant, but breaks supersymmetry. I'm going to have a coefficient there, and I'm going to call that coefficient little d. AI. There's lots of different choices for these. I'm going to pick a very specific one in what follows. So
Wait,
this,
is this the most general relevant, non-supersymmetric relevant definition you could put in the theory?
I don't know. It's given that particular multiplet that I wrote down.
Yes.
Yes. Are there others that sit in other multiplets? I don't think that's.
There's no other short multiplet.
That's right.
Which has a non-supersymmetric deformation in it.
That's right. In fact, I'm fairly sure there is another relevant deformation for a reason that I'll tell you shortly, but I don't have any control over it. But these are the ones I have
I
control.
want to keep it short so that we know something about it.
But if it is the direction, one that's the direction.
But we wouldn't know, right? I mean, we know the spectrum of short of BPS operators, so we know everyone in their multiplet, and then we could anything else may or may not exist. How would we know?
All right, so HA, I'm going to take in a very particular direction. And the direction is going to be this unit vector V hat A. So for example, we'll pick the unit vector to be 0, 0, 1. And then H can be positive or negative.
Preserve one U1 even with the second one.
Sorry, say that again?
You can continue to preserve this U1. This vector preserves one U1.
It preserves the U1 out of SU2I.
With the choice of DAI, you can choose DAI suitably so that you preserve that.
And that's exactly what I'm going to do. Yeah. There's actually other choices. You could lock the A index, so you could preserve an SU2 diagonal out of SU2R and SU2I. So there are other things that one can do that I'm not doing. But let me just write down the final one. So for this, I will. Oops. I'll take it to sit in the same direction in SU2I space, but it now also is a new direction in the R symmetry space. So just as you said, Indranil, they preserve the same U1 in SU2I.
So these stick ones that you talked about, do they preserve some supersymmetry?
Sorry, which ones?
The ones in which you solder A and I.
No, they break all supersymmetry. Yeah.
Even if you preserve a diagonal SU2,
Yeah.
that will not be
Yeah.
one in some two steps.
I don't think so. So,
Sorry, David.
yeah,
I'm
please.
asking Abhijit's question.
Yeah.
What about the multiplet with the stress tensor? Since the stress tensor has dimension 6, anything, and it's built by acting supersymmetries on some primary, all of those primaries have lower dimension than 6. Is there no scalar in that multiplet?
Dimension 5.
5 with 5.
I don't know.
Maybe, what is the primary for that multiplet? Is it a current or a scalar?
Well, if it mimics 4D and equals to 2, it should be a scalar.
I see. There could certainly be other relevant operators. Yeah. Okay, what do we have here? We have that the SU2I symmetry and the SU2R symmetry are broken to U1I cross U1I. All right. What I'm going to do is just as for this deformation I picked a direction, for this deformation I'm also going to pick a direction. So I choose a U1R out of the SU2R. And what I want to do is extend this phase diagram. So that's my supersymmetric fixed point. This is the H direction, which takes me to super Yang-Mills. I also want to understand what happens to the phase diagram when I turn on the mass.
I'm a bit confused. Sorry, you picked directions. There were 3 directions in the game, right? The direction for your.
The SU2I1 was the same for both. That's this unit vector V hat.
Okay, so let's say that's the Z direction in SU2I.
Yeah.
And
Then I get to pick a direction for
some
SU2R.
direction, which we can call the Z direction in SU2.
Exactly. Yeah.
So the phase diagram would consist of unlocking this also. Unlocking the two directions.
Oh, the fact that I could have just as easily. There's no connection between them.
Not that the VAV, you could unlock it.
It's already unlocked. I mean, you could either have a SU2 diagonal left unbroken
Mhm.
or just down to U1 cross.
No, but he doesn't want to preserve supersymmetry lengths at all. He
So
wants
I want this symmetry group
Right.
preserved at the
Yeah.
end.
Yeah, okay.
Yeah.
So that symmetry would distinguish that.
Yeah. And moreover, by this symmetry group, I really mean a specific U1R within SU2 and a specific U1I within SU2. So I'm allowed to project it here. And we'll see shortly why this is useful. So that's the goal. Fill out. Yes.
What's going on, but just, of course, there, as has already come out, there are other things you could do. For example, break the U1R also
Mhm.
and then keep the diagonal on.
Yeah.
Is the claim that you can analyze all of them and you don't flow to something?
No. The claim is I have no idea what happened. Actually, it's not quite true. The one that locks the SU2I and the SU2R, there is something you can say because the SU2R has a non-perturbative Z2 anomaly, and the SU2I does not. And when you put them together, there's also a non-perturbative anomaly. So wherever they flow has to preserve that anomaly. So what can happen? Either that symmetry can be spontaneously broken, that's interesting strong coupling dynamics, or there are massless fermions in the game to preserve it. Most likely the latter, I think. So you have some very minimal control if you do other things.
So sorry, is the following claim that there is a mixed anomaly in the super conformal fixed point? There is a mixed anomaly between SU2R and SU2I?
No.
That's not a
No mixed anomaly. SU2I is anomaly free. SU2R has a non-perturbative Z2 anomaly.
SU2R has a non-perturbative Z2 anomaly. That does not involve any. That might have stress tensors. Asymmetry might have mixed anomaly stress tensor set, right?
Don't think you can have the mixed anomalies for SU2s. You could plausibly have them after you've broken down to U1s, but and in fact these things will emerge, but not before.
Only when you break it to U1s, then you said there is a mixed anomaly between U1I and U1R.
We-
Statement. When you break down to U1I times U1R, what is the statement of the anomaly?
We'll see.
Okay.
Yeah, we'll see. This is going to come out. Yeah, but if you do the other one where you try to lock the two, then there's a non-perturbative anomaly for this, no anomaly for that. Locking the two retains that non-perturbative Z2
And
anomaly.
when you say non-perturbative, you mean some global anomaly.
It's a global. It's a pi 4 anomaly for All right. So what I want to do is fill out the picture on the right-hand side of the board, understand where we flow in general. All good. So we have almost no control. The only place we have control is a weak coupling. So weak coupling.
And what are those two axes? These again, H and D.
So this is H.
H and D.
M. Yes. M is.
M is Y axis. The VA was a unit vector. Right?
VA was the unit vector that picks my direction in SU2I. All right, so the only place I really have control is weak coupling. Weak coupling means, which way? This has dimension 2, this, yeah. I think this way. No, the other way. All right. Means what? Weak coupling means I flow, but in such a way that I come very, very close to super Yang-Mills, where I understand what happens, and then I turn on this supersymmetry breaking deformation. Now, the advantage of understanding where this came from and the fact it was in a short multiplet is that I can follow what this supersymmetry breaking deformation is in the super Yang-Mills theory. So, what is it? You go back to the super Yang-Mills Lagrangian, and there's the MI, and it's just mass terms for the scalar and for the fermion.
So, when you pick this M
Mm-hmm.
in a particular direction,
Yeah.
the special point is when it is parallel to the to the B.
No, because the SU2R and the SU2I know nothing to do about
No,
each
but
other.
that would preserve more symmetry, right?
No.
So what does one mean by Tongkian then?
No, that was an entirely different discussion. It was a different deformation.
That would be DAI is delta A, right?
Yes, it's exactly that. Thank you. Yes. Yeah. So with this deformation, there's no sense of locking.
No, but that's what I was saying. So mu, when D, if it's parallel to VA, that would be proportional to no.
No, it would be D33 is something and D11 is 0. Yeah. All right. So, in this weakly coupled regime, it's very clear what happens. You just give a mass to the fermion and the scalar in super Yang-Mills. The mass for the scalar is coming because it hits the D term. When I integrate out those D terms, I just get a phi squared term for the mass. So here it's completely trivial. If I turn on a mass, I flow to actual Yang-Mills. I don't give a mass to the SU2 gauge field, I just give a mass to the fermions. That's true if I flow here with a mass positive or negative. It's true if I flow directly to there and then turn it on, and it's also true if I flow this way.
Roughly, how did you know what mu AI maps to?
Oh, you can think about this in the following way. You take the SU2 symmetry in the theory, and you weakly gauge it. This term here is like weakly gauging a U1I in SU2 and giving a vev to the scalar in the resulting vector multiplet. This one here is like giving a vev to the D term in the vector multiplet, which is why it breaks supersymmetry. Okay. It's also why it's called little d. So then you can do exactly the same here and follow it through. This
And
is
there's
what you
also
get.
probably just a unique operator with that symmetry assignment that is relevant.
No, because you've lost the SU2 by the time you've flown. You've only got the SU2I, you've only got U1I, and each of these operators individually would have worked. So I said earlier, I think there is another relevant operator. We know for sure that when you're here, there's another relevant operator. So there's another direction one can flow in.
But the Yang-Mills theory by itself can just be close to the free.
And then that's just a free theory. So it looks like, we've only said something completely trivial. It also looks like I've just repeated myself 4 times for no reason at all. But what I want to say is that there is another bit of information that we have about what's going on. Are there any questions about this so far?
And is there any information about what you get when you set h to 0 and just turn on m?
That's the interesting question. What happens here? That's where I'm going. Yeah.
So far, we we go to super Young-Mills. If we go like this, we go to Young-Mills. And this is the statement. If you stay close, then you follow that trajectory.
Yeah.
So far.
Yeah.
Close is probably anything non-zero.
Close, yeah, what does close mean?
This trajectory is not, I've always insisted that A square is greater than M, so you float roughly like parallelly, not
Yeah.
exactly but roughly parallelly, and then you follow that.
Yeah, that's right. So far, there's no paper that can be written with these results alone. Yeah, that's just not interesting.
Just to take the comment you made that you could have just started from the super Young-Mills and you would know you have these two deformations. You could also then just, since you're breaking SUSY, just turn on phi square, for example,
Exactly.
etc. So
Yeah, and that would be there's even more.
deformation.
And that, if there's a relevant deformation here, I suspect there's another relevant deformation here. Might not be the case, but it seems like.
The scalar has also become massive. That's really just pure Young-Mills then?
Pure Young-Mills. Scalars become massive because it multiplies the d term. There's a d squared term. Okay. I can do something non-trivial now.
Right. So that term is exactly something, the phi d.
Yeah. So I can just do these. I could put different coefficients here and here. They're the Sandip's terms.
I guess phi cube is already irrelevant.
Yeah, everything's irrelevant in 5D. Yeah. All right. So what's the novelty? The novelty is that to flow here, I had to integrate out massive fermions. And in odd dimensions, massive fermions are interesting because when you integrate them out, they leave behind a memory, even when they become infinitely heavy, of what they were, and they leave this behind through Chern-Simons terms. So there may be a way in which we can characterize the topological phases of the massive fermions in these four.
Care about the directions,
Yes, it will. Yes. It'll care. So, sign of the mass of the fermion is going to be important. So here's the idea. What we're going to do is add background gauge fields. So these are not dynamical objects. These are fixed things under our control. And we're going to add them for the two U1 symmetries that we had. So we're going to add an AR and an AI. These are background gauge fields that couple to the U1R and the U1I currents. When I integrate out the fermions, I'm going to generate Chern-Simons terms for these background gauge fields. Chern-Simons terms for background gauge fields characterize the response of the system to various things. In 3 dimensions, the Chern-Simons terms are quadratic, therefore they characterize linear response. In 5 dimensions, the Chern-Simons terms are cubic, therefore it's going to be some nonlinear response. I don't really know what this response is physically, but just knowing that it's there is going to give me a way to characterize these phases. So the Chern-Simons terms that I care about are the following. Actually, these are not the most general, as I'll...
You could turn the non-linear response into a linear response with an additional background field strength. Could you?
That's true. You could think about it as linear response in a background of something non-zero. Yes. Yeah, exactly. All right, so these are the Chern-Simons terms I'm going to have. They're not the most general. There's also mixed Chern-Simons terms in which I have an AR and an AI and an AI. We can also calculate those, but for the purposes of this talk, it will be sufficient just to tell you about the diagonal ones.
Now it is very important that your fermions are sort of symplectic. Because Dirac fermions would have a different kind of mixed anomaly with time reversal.
That's right. Yeah. No, it took us.
This is why
It took us months to figure out what a symplectic Majorana fermion was in 5 dimensions.
This is
Yeah.
why you kept on saying Z2.
Yeah, exactly. Yeah. So we'll see where this Z2 comes in now, but it's precisely because these are symplectic Majoranas. All right, so this is the goal. In each of these quadrants, I want to figure out what the background Chern-Simons terms are for Ki and Kr. Okay. like I said, I could do more. There's also mixed gravitational ones, mixed gauge. There's a whole bunch of ones that I'm not discussing, but I'm just going to tell you these. One of these is easy to do because it's just perturbative. So if I'm in the weakly coupled limit, I can trust perturbation theory. So that means if I'm over here, I just integrate out the fermions in the action. I generate a Chern-Simons terms at one loop. It's a nice triangle diagram. The Chern-Simons term you generate is for Kr, and it's -3/2. In fact, it was already said times the sine of the mass. The 3, because these are in the adjoint of SU2, so there's 3 of them. The half, because Chern-Simons terms always famously come with a half. The fact that the end result is half integer tells us that there's a parity anomaly for the U1R. This you can trace to the existence of the non-perturbative anomaly for the SU2R. So the Z2 non-perturbative anomaly for SU2, once you break it to U1, becomes a perturbative parity anomaly, becomes something much more familiar.
Sorry, I'm sorry. You have 2 U1s, right? Is there in any sense that you can use some sort of a combination and only that combination has an anomaly and the other combination is free?
Yeah, no, we have all the mixed ones, so the answer is no. They both have anomalies. In fact, by the time I've drawn what I'm going to draw, we'll see why that's true.
Because this is just a sum, you said. There is
Yeah.
no mixed.
No, there is a mixed one. There's which one is there? There's an RRI, but not an IIR. So there is one mixed anomaly. Because the instantons carry R charge, but the perturbative ones don't carry I charge, which we can calculate, but it doesn't allow you to remove one of them. So they both have anomalies.
And just to check an SU2R rotation can change the sign of N.
Yeah, let's do that actually. Let's see how that works. This is going to be an important part. So for each of these I want Ki and Kr, and we've just computed what they are. It's -3/2 here, and plus.
But because it also changes the sign of A, presumably,
Good.
it's allowed to have a Kr, but it won't be allowed to have Kr.
Very good, yeah. So let me translate what Shiraz said. Shiraz says that I can move smoothly from here to here, not by going through this line, but by rotating U1R and SU2R. U1R and SU2R rotates, well, that U1 gets rotated within the SU2. By the time I come down here, it's come back to itself up to minus itself. But if I do minus here, because this is cubic, minus AR, AR goes to minus AR, flips the sign of this. That's another way to see why the sign is different between plus and minus. This argument's going to be very useful shortly because I'm going to want to relate things here. All right, so that's the simple perturbative one. What's next is the non-perturbative one. To get Ki, remember the objects that are charged under the U1I are instantons. They're non-perturbative states. So we can't just do a perturbative calculation to determine this. We need something a bit more subtle. I'll give you a very glib explanation of the something subtle. Are there any questions about this so far? All right, so I think, and I apologize, for the next 2 minutes, if you haven't studied SUSY gauge theory in 5 dimensions, it might be a little bit tricky to follow. The action of supersymmetric gauge theories is specified by a prepotential. And the prepotential it's exactly like n equals 2, except it's much easier. Remember, n equals 2 is tree level plus 1 loop plus an infinite series of instanton terms that Seiberg and Witten had to do something very clever to get. 5 dimensions is tree level plus 1 loop plus nothing else. So it stops at 1 loop. It's much, much easier. Certainly, if you go out onto the Coulomb branch, you can just do a perturbative calculation. And it's very simple. Even I can do it. It's that simple. So what do we have? The pre-potential is, the tree level term is this. H, remember, is 1 over g squared. So that's why this looks like a tree level term. If you do one loop, you get this. This one loop term is phi cubed. If you expand it out, it gives a Chern-Simons term for the U1 gauge field that lives on the Coulomb branch. But a Chern-Simons term for the gauge field, not for the dynamical gauge field, not for the background gauge fields that we need. What we noticed is that,
Sorry.
yes,
This is directly in the Lagrangian?
this is from the Lagrangian. This is the Lagrangian for this theory on the Coulomb branch. What we've noticed is there's another term which only involves the background fields, which is H, and has to be there so the entire expression is invariant under the duality symmetry that the theory has. Now, we were very excited about this, but on Christmas Eve, Kim Yong-lee and his friends put out a paper that also points out you can have these extra terms. So we got scooped because we were too busy eating turkey over Christmas. So there's an extra term. This term here, if you expand it out, gives a U1R cubed Chern-Simons term. So you can extract the coefficient of the U1R cubed Chern-Simons term from the supersymmetric completion of this term in the pre-potential, but a term for a background field rather than a dynamical field. And the answer is Ki is minus 2 times the sine of H, which means that we get to complete this. Sorry, somebody. Yeah, please.
Getting this pre-potential must be non-trivial, right?
No, you just need that it's invariant under H goes to minus H and phi goes to phi plus H. This is the duality symmetry that you use to fix this term. Oh, there's one other thing. You have to argue that the H squared phi term vanishes.
Sorry. So if I want, this is supposed to be the effective potential that we are getting after all this, right? So I mean, why is it that there are no loop corrections and so on?
Oh, there is. There's a one loop correction
One
here.
loop correction and not further. What was the argument for that?
Oh, this is Seiberg's argument from the 90s. There's nothing that can do it at weak coupling. There's no non-perturbative. It's one loop exact, yeah.
Also, there is no star of instantons. That was also.
No, the instantons are BPS particle states in 5 dimensions. They're not like in Seiberg-Witten where they're contributing to the effective action.
But where is the H cube coming from the point of view particle?
No, it's got no dynamical fields in there. It's just background fields. So usually one ignores it. But now precisely what we want is the effective action including background fields. This is the term that
Some contact term would go to it, that's right.
I guess one could say it that way. Yeah.
So it's always hard to figure out.
So there you write U1 cube R or I?
Sorry, that's oh, my bad. Yeah. All right. In fact, you can get the mixed Chern-Simons terms using a very similar argument.
But would you not expect after reducing this on a circle to get a potential of n equals to 2 which has the space integrals also?
Then you have something harder, right? Because you have to start those BPS states can go around the circle and then they become instanton contributions and then you do get the Seiberg-Witten, but it's not straightforward.
This is 4 plus 1.
This is 4 plus 1 non-compact. Yeah, exactly. All right. Now we can redo what Shiraz suggested and just check how this works. Shiraz suggested we do an SU2R transformation to take us from here to here. But we can also do an SU2I transformation. An SU2I transformation, because that V hat was in both terms, takes us from here to here. It flips H to minus H and M to minus M. It also flips the sign of the first term, but not the second, which is why the minus goes to plus, but this minus stays the same. So this is what the phase diagram looks like if you include the background Chern-Simons terms for these two U1 global symmetries that we have.
How does the minus 3 halves in the third important Archimedes theorem formula for KR that was minus 3 halves?
Yeah, there's something interesting here. What happens? The UV deformation is, let me put V hat A plus MI, V hat A, UAI. All right, this was the UV deformation. The IR deformation also includes a mass, and when I wrote it down, I identified the mass in the IR with this mass in the UV. Turns out that's not quite true. The mass in the IR is the sine of H times the mass in the UV. And it's this extra sign which gives you this. It's not so unusual because 1 over G squared, which is the IR gauge coupling, is the sine of H times H. So it's perhaps not so surprising that happens. But that's why there's a minus there and a plus here.
David, bringing up the previous point about this diagram being should actually be drawn on a sphere. How should I think of this particular low energy theory on a continuous?
You see, I've written down these Chern-Simons terms for a fixed U1 gauge field. If you're thinking about the sphere, you're now rotating what the U1 symmetry means within the theory. And by the time you get to here, your U1 gauge field itself has flipped sign, which is why I was trying to say earlier, it's not such a good way to think. Fixing the U1 theory gives you extra information. What the low energy effective theory is for background fields with fixed U1s, not allowing U1s to rotate.
David, this is perhaps, I don't know, either remedial or something you'll come to, but is there interesting dynamics in the super Young-Mills with the Chern-Simons theories terms in 5D, or is it still just a free theory?
The very interesting dynamics, but for SU2 there is no Chern-Simons term. For simple, you mean for the gauge field, Chern-Simons terms for gauge fields.
But
yeah.
Here, even though these are backgrounds, I see.
This is for U1 because we're on the Coulomb branch. This is background. But for SU2, just for this DABC thing.
Okay.
Yeah, the same reason there's no anomaly for SU2 in 4 dimensions. The Witten anomaly is there, but there's no perturbative anomaly.
But even dimensionally, Chern-Simons terms 5 dimensions is more irrelevant than the Yang-Mills term. So you would expect it not to modify the IR.
That's true, but that's right, but it does modify the UV completion.
Yes.
Yeah, and so there is a big story about SUN, N3 and above, with Chern-Simons terms and what Chern-Simons term you can have and what the fixed points are. And people who know these things know these things.
Yeah, but in 3 dimensions is really special because the most relevant operator.
Yeah. All right. So now we have something a little less trivial, and now we're basically done. What's the deal here? We've specified the low energy dynamics. It's just Yang-Mills, but with particular coefficients for these background Chern-Simons terms. And these coefficients should be integer, or at the very least half integer, because you have parity anomalies. Now we ask, what happens as you move within this phase diagram? It's SU2 Yang-Mills everywhere as far as we know. But to move from here, well, actually, let me do a trivial one first. Suppose I want to move from here to here, and I don't want to do what Shiraz says, which is rotate. I want to keep my U1 fixed. In other words, I want to move in the plane of the board. Well, the Chern-Simons term for the first one is the same, but the Chern-Simons term for the second one jumps. And the Chern-Simons term jumping in this case is signifying that as I move, I get new light states in the system. Now, the light states are totally trivial. The light states are just the massless fermion, and it turns out for supersymmetry, the massless scalar, which appear at the super Yang-Mills theory. So the jump in the Chern-Simons term is signifying I have new light states charged under U1R, which appear as I cross this axis.
This is a second order phase transition.
Here it's a second order phase transition. So now the question is, what happens if I sit here and I move from this quadrant up to this quadrant? In doing so, I go through the region that I have no control over whatsoever. I go through the region where H is 0, but I just turn on M. But something interesting has to happen. It can't be that this just flows to a gapped system. It can't be that this flows just to SU2 Yang-Mills. Something novel has to happen because both of these Chern-Simons terms have to jump. So what are the options? There are interesting options and less interesting options.
Could you repeat why is it that this indicates the presence of massless?
Well,
Here we know, because we know on that line.
here we knew exactly.
Just changing of this thing.
A phase transition.
It's a phase transition is all. I'll give you the options, and the more interesting one is massless. So what are the options? The options are first order. No, I'm not saying it necessarily gives rise to massless fermions. I'm saying in this case we know it does. In this case, something interesting has to happen, and now I'll just list them. And I think the most interesting is massless states. Okay, so it could be a first order transition. I have to confess, I don't have this fully understood in my mind. The ground state has these Chern-Simons terms. The suggestion is that there's another metastable state in the system that has these Chern-Simons terms. And that as you move across here, just as in basic stat mech, the energies of these two states change. At this point, there would be two degenerate states, and over here, this one would become the ground state. I have no way to rule this out whatsoever. It would mean that when you're here, there's two degenerate ground states. Now, two degenerate ground states usually appear because there's a symmetry which is spontaneously broken, and I think the symmetry is the duality symmetry.
I'm really confused. The two correspond to the different values for H, right? Those two.
Yeah, that's right.
So they're not metastable in the same theory, right? H is a background.
No, I'm suggesting that here there may be a metastable state here. And then as I continuously change H, as I change H, the metastable one becomes stable, and then.
But you don't see it directly in a sense flowing that way.
And you know, it doesn't exist here, but metastable states typically have a spinodial point beyond which they don't exist. So it may be that the state appears to be metastable here, and then.
But I mean, it may be that it's just not metastable at all. I mean, it just appears as a stable state.
Oh, we'll come to this as we go on. Yeah.
More interesting things could also happen because your arguments about those numbers really cared about H being very large and then you float.
Yeah. So I've basically got control here.
Right. So it might be that there is one interesting point where this symmetry is less spontaneously broken. There could be more interesting situations, right? Because in the neighborhood of this vertical strip, you don't know exactly how many tests.
There could be 17 phase transitions.
Right.
There's an odd number though. I know that because of the symmetry of the system. So let's look at what else is possible. Another one is that U1R and U1I are both spontaneously broken by strong coupling dynamics. That kind of just takes the symmetry out of the game, and you no longer get to talk about Chern-Simons terms. This would have to happen in a phase. You can't have spontaneous breaking just at one point. So there'd have to be some kind of phase here in which these two symmetries were spontaneously broken, and there were Goldstone modes. Okay, so sort of interesting that 5D strong coupling can do this. Not the most exciting thing in the world. It would just be SU2 coupled to a couple of Goldstone modes. However, if you assume the symmetries are unbroken, things become much more interesting. Because if the symmetries are unbroken, then just as there are here, there has to be a second order phase transition and new light fermionic states that appear at this point, so that when you integrate them out, the Chern-Simons terms jump. Those states have positive mass on one side, negative mass on the other. The Chern-Simons terms are jumping. What's interesting in particular is that because the U1I Chern-Simons term is jumping, these are non-perturbative states. So these are instanton-like states which are becoming massless even though you're in a non-supersymmetric theory. So massless U1I states. If that's true, there's something interesting that happens here. This is our candidate for a non-supersymmetric fixed point. The evidence, I think it's fair to say, is meager, but it's certainly clear that something interesting happens on this line. You can then ask, if it's massless states, is it interacting or is it just free? It seems to be possible that it's just SU2 coupled to some fermions. However, the states are non-perturbative. It's in a regime where everything was strongly coupled here. So you might hope that really it's some novel interacting fixed point. Whether that's true or not, I have no idea. But this is the evidence that we have. All right, I'll stop there. Thank you.
Questions? So does the mixed Chern-Simons term also change across this?
Yeah. Maybe I'll just. I think it goes with the sign of H. Yes. So yeah, it definitely changes across that line. Yeah.
So how did you rule out these other two options? I didn't quite get.
No, I didn't. These are the options, and I don't have any way to rule these out. Yeah.
Anything interesting happened? This theory had SU2, Yang-Mills theory.
Mm-hmm.
Is there an SUN version of your story?
No, things. What did we need? Let me say almost certainly, and I don't know what it is. Yeah.
Maybe you could use gravity or something into that. I mean, if you take n large.
Oh, I see. I see. Are there There are ADS6 solutions that were discovered at some point.
Yes. Thomas Cielo.
Yeah. I see, maybe. I think what happened, we did look briefly at, we wanted ones that had this SU2R symmetry, that this somehow was simple just to help us rotate things. But the parameter space was much larger. The phase space, the phase space of the system that we had to consider wasn't two-dimensional. When we looked at SUN. There's a very specific theory, SUN with Chern-Simons level n/2, and blah, 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 that has this enhanced SU2I symmetry. When we looked at that, it seemed doable, it just seemed significantly more complicated than what we had.
To ask slightly another version of that, if you started with more supersymmetry, although of course you want to break it finally,
There's no such thing as more supersymmetry.
there's no such thing as more supersymmetry.
Well, you go up to 6 dimensions. So maybe one could start with the 2, 0 theory to think about breaking that. But we haven't.
Could the Lagrangian be just that of 5 Chern-Simons here interacting with a bunch of massless?
Here?
Yeah.
Not Chern-Simons, because it's SU2 is everywhere in this phase diagram, SU2 Yang-Mills, and there's no Chern-Simons theory for that. I think it could be SU2 interacting with fermions. Yeah, it could be free still in the infrared. It could be free in the infrared. I can't rule that out.
Oh, you're saying there's no such thing as an SU2 version of the 5 Chern-Simons?
DABC is anti-commutator of sigma 1, sigma 2 times sigma 3. It just vanishes.
In other words, since SU2 is SP, but anyway.
That's the fancy way of saying it.
But is there an SU3 version of the Chern-Simons?
Yeah.
So maybe when you go to higher end. Abhijit's point is that it looks like the gauge coupling is going to 0, right?
Yeah. Oh, I see.
So
That's why you want
zero,
just
pure
Chern-Simons. I see.
That sounds like a very interesting one.
But not for here.
Yeah.
But it's that intuition which makes me. And that, and I want an interesting story rather than a boring story, but that suggests this might be a strongly interacting fixed point rather than something free.
No, but that could also be an interacting fixed point, right? With the SU3 place where you could have Chern-Simons, you could write down Chern-Simons.
If it's Lagrangian, it's free in 5D.
Why?
Because all terms you can write down that are interactions are irrelevant.
No, Abhijit's saying, suppose we were an SU higher than 2. And that there was a Lagrangian description of that, which was no Yang-Mills, pure Chern-Simons, interacting momentum. That is far from free because there's no kinetic term, there's no quadratic term for gauge.
No, but I thought, sorry, but I
Doesn't it
thought-
just generate it as you?
Yeah, that's what I was going to say.
Doesn't it just generate it as?
Why doesn't it jump? Exactly what I was going to say. I thought your point was the SU2 kinetic term is, the gauge kinetic term is more relevant.
Yeah.
No, but you're tuned to the point. Where in the IR, that's not there. That's
I see.
In other words, flop. You could flop with this Lagrangian.
yeah,
Isn't the same thing?
right. So just to say it again, I mean, it's true that it would generically be generated. That's why you have to do a one-parameter tuning to make sure it's not.
Which of course is what's happening.
I mean, the theory doesn't sound totally well defined, perhaps, but it sounds very interesting. Didn't Witten look at this theory for M theory lifts of these knotted variants? Yeah,
I don't know that.
I think he did. But
In the supersymmetric.
supersymmetric version, but it might be worth looking at. That sounds very interesting.
It's only got 2 derivatives, so it's clear it's poorly defined.
Well, the problem with it is that it looks like if you take just the Yang-Mills part, the Hamiltonian is 0 because it's topological. But the equation of motion doesn't force your solutions to be pure gauge. So it looks like you've got an infinite dimensional phase space at 0 energy. Now the matter may change that, but it looks very looks at the edge of being well defined.
I see.
This is Abhijit's favorite theory. We've talked about it for the last 6 years.
Might be time to do something.
So at point, I heard you had mentioned gravitational anomalies in this theory. So have you tried coupling this to some gravity and look at the anomalies?
We looked at A wedge, R wedge R. And there's different A's you can put here. You can put the gauge field itself if you're on the Coulomb branch. You can put R and you can put I. The R one you can compute perturbatively. The gauge one you can compute perturbatively. And then it turns out the gauge one you can relate to the I current one through this kind of pre-potential like argument. But that's all we've done.
So where is this presumably breaks parity, right? The Chern-Simons term.
The
Gauge
mass of the fermion broke parity. Yeah.
So, but at 0 1,
No,
if I,
this breaks parity. Preserve T and CP, but not P.
oh, that line breaks.
Yeah. Yeah, this one doesn't.
So it could, yeah.
So why is it that this line is?
This is just the supersymmetric line.
That's
Yeah.
If you just turned on a mass for the fermion
Mhm.
without explicitly putting the phi di term, so the scalar mass term, so that would not be supersymmetric. But I'm saying that the scalar anyway will get a one loop mass from the fermion mass at tree level, and so that much of this stuff will probably be.
So everything would hold at weak coupling.
Yeah.
I just wouldn't be quite sure I could follow in here. Whereas with this particular deformation, I know that yeah, this 2-parameter phase space is okay.
So super YAMLs on these two sides, they do not have any string theory embedding. Is that right?
Well, they have hundreds of string theory embeddings.
I see.
Yeah, brain diagrams, I think
I said that.
Seiberg probably got them by brains probing certain singularities. There's thousands of papers
No,
on this.
but I mean, the point of my question was because there's a gravitational anomaly appearing when you deform the theory. The deformed theory won't have any string theory embedding because it's anomalous, right?
No, it surely does.
No, I mean,
Because it's a deformation of the supersymmetric theory, so if one can just find that deformation and control it in a string theory setting, which is the hard thing, then it should be
actually, I
fine.
was referred to a paper by two of your collaborators, I think a couple of weeks ago, showed that some super YAML series for sufficiently higher rank gauge groups cannot be consistently coupled to gravity.
Oh, I see. Sorry, my bad. So that's a question of coupling to gravity. That was n equals 4 super YAMLs in 4 dimensions.
Yeah, in 4 dimensions.
So here it would be.
I mean, there was a specific example, and
Yeah.
they call the string lamppost principle, and I think their point was much more general that for some d-dimensional theories, that the rank of the gauge group can at most be 26 minus.
Yeah. Well, one could certainly ask if it's possible to couple this to 5D gravity. Does that anomaly prohibit it? I don't think so.
I mean, I'm not sure. Probably the question is rather ill-defined. So as
Well, the supersymmetric theory you got could be obtained from some brain thing, right?
But they're always with gravity in higher dimensions, never gravity in 5 dimensions.
I see. Okay.
Yeah. It's a question about compactifying the space and not having tap hole.